Mhm.
So this would be very. Yep, I added these two.
Right.
And that gave me this,
Oh, okay, then. And then you subtract. That's okay.
subtracted the 2.78
Mhm.
minus that number, the 4.61.
Mhm. And that gives the methodology, right? So what you're gonna do now is, based on, remember the steps we went through, where you, I did it in a tabular form, where, you got the masses first, you convert them to moles,
Okay.
and then you divide by the lowest number of moles.
Number of moles.
Right, and
Okay.
then that gives you the simplest ratio, and then that should give you ultimately your empirical form.
This would be grams of O2.
No,
correct?
just
Okay.
it's not oxygen by itself. Okay, let me take roll first. What am I doing? Okay. Amo. Bessie is here. Bishop. Here. Brad.
Here.
Cornell.
Here.
Chestnut. Forward. Erlandson. Gerard. Green. Kennedy. Leonard is here. Mohammed Boy is here. Spall.
Here.
Solomon.
Here.
And Swissa. What's your last name? Robert. All right, so, we're gonna start chapter 4. And chapter 4 deals with aqueous solutions, I'm sorry, reactions in aqueous solutions. So let me bring up, well, let me share my screen first. We bring up the PowerPoint.
For the last time, are we doing the percent water in the picture? What are we doing?
No, percent, hydrate, yeah. Okay, so, we're gonna look at what happens when it comes to reactions in aqueous solutions, and most of these reactions involve ions, at least as being reactants. And in order for us to understand these types of reactions, we need to understand the nature of ions and the electrical properties associated with such solutions that contain ions, right? So of course, there are two types of ions. You have positively and negatively charged ions. And basically, you need to understand the nature of these charges. Simply put, basically, like charges will repel each other and unlike charges will attract each other. And of course, in terms of any particles that have no charges, there will be no attraction, at least no attraction based on the electrical properties or the charges that are non-existent here. So what this particular diagram demonstrates is basically how the charges behave with respect to each other. In this situation where there are no charges, there's no forces of attraction or repulsion. In this case, it's where you have two unlike charges in close proximity, they'll be attracted to each other. And then in these two last cases, where the charges are like charges, they will repel each other, right? So it's kind of similar to bar magnets. I'm quite sure we have all played with bar magnets as kids, right? And you know that each bar magnet has a north and south pole. If you try to bring like poles close to each other, they'll be repulsive force. If you put together like and unlike poles, like north to south, then basically attraction will take place. So that's basically the nature of charges, all right? Now, what we're going to talk about here is basically the effect in terms of conductivity that ions will have on the solution that it's in, right? In fact, what we're talking about here are either solutions of ionic compounds, or if you have the ionic compound by itself, but it's molten. And what that means basically is that the ionic compound is in a liquid state, right? In order for you to achieve that, of course, because it's ionic, you have to heat it to a very high temperature, right? So if you take a compound like, let's say sodium chloride, in order for you to convert it to a liquid, you have to heat it to an extremely high temperature. I don't remember exactly what the melting point is, but if I recall, I think it's about 400 degrees Celsius. So, in either case, when you either heat your ionic compound to a liquid state, or you dissolve the solid ionic compound in water, what you're going to end up with as a result are free floating ions, right? In either the solution or the molten compound. And whenever you have free floating charges, not only ions, but electrons and so on, there exists a possibility of that substance being able to conduct electricity. And that is no less true for this situation here, right? So what is being shown here is a situation where you have either a molten ionic compound or the ionic compound dissolved in water. The ions are free to move around, and then you have two metal plates. They are called electrodes, and these electrodes are connected to an electricity source. So you basically an electric current. I don't know if you know this, if you haven't done any physics from before. An electric current is formed when you have charges moving in a particular medium, right? In the case of the external circuit right here, the charges will be in the form of electrons, right? So what happens is that because the electrons are flowing in this direction, this here electrode becomes negatively charged. This electrode becomes positively charged. So what will happen is that the positive ions here will be attracted to this electrode. And by the way, the negatively charged electrode is called the cathode, right? And the positive ions will be attracted to the cathode. And that's why the positive ions are called cations, because they're attracted to the cathode. On the other hand, over here, where we have the positively charged electrode, it will attract the negatively charged ions, right? So therefore, that's why the negatively charged ions are called anions, right? So the result is that not only do you have an electric current passing through the external circuit, but you also have an electric current passing through the either molten substance or the substance in a solution, right? And that's one important property of ionic compounds. Ionic compounds will conduct electricity either in an aqueous solution or in a molten state, right? So that's basically it as far as the electrical property of ionic compounds are concerned. You will never have that happening in the case of a molecular compound, even if it's solved in water, like for example, sugar. I think we're gonna have an example of that shown coming up later. But if you, let's say, dissolve sugar in water, it will not conduct electricity because sugar does not break up into to form ions. So you won't have any free floating ions in a sugar solution. All right, so the anode is, as I said before, positively charged. The cathode will be negatively charged, and therefore you're going to have the attraction of the negatively charged ions to the anode, the positively charged ions to the cathode, and therefore, as a result, an electric current flowing through your solution or molten compound down here. All right. So this is an example of what I just mentioned earlier in passing. Methanol is a molecular compound which, when dissolved in water, does not split up to form ions. So as a result, it does not conduct electricity, right? So this is basically a picture showing you the demonstration that methanol will not conduct electricity. Basically, we have your beaker with methanol. You have two electrodes here. You have wires leading to the electricity source, and you have a lamp here. The lamp basically indicates whether or not the current is passing through. As you can see, the lamp is not lit. I'm sorry. So therefore, that indicates that there is no current passing through. So basically, we call this a non-electrolytic solution or non-electrolyte solution, right? And again, that's because there are no free-floating ions present in this solution of methanol. On the other hand, if you take sodium chloride, dissolve it in water, right, and put the electrodes in, flip the switch, then you're going to see that the lamp here lights up very brightly, right, which indicates a flow of electric current through the external circuit, right? So therefore, we say that solutions such as sodium chloride, which allows for an electric current to pass through freely, we say that that's a strong electrolytic solution. And then on the other hand, you have somewhere in between where you have some solutions that they do allow an electric current to pass through, but not as easily as in the case of sodium chloride. An example of this would be acetic acid. Acetic acid will only partially dissociate. And what that means basically is that most of the molecules will not break up to form ions. So if you could actually see the particles present in the solution of acetic acid, you're going to see, in addition to water molecules, you're going to see mostly acetic acid molecules and very few ions. The ions would be the acetate ion and the hydronium ion, right? So because of the relative low concentration of those ions, the solution won't conduct electricity as well. And therefore, if you look at the lamp right here, you see that it barely lights up, right? So it indicates that there's a current passing through, but a weak current, right? And that's because the solution that the current is passing through is what we call a weak electrolyte, and therefore they are poor conductors of electricity, right? Okay, so those are the three categories of solutions in terms of their ability to conduct electricity. Strong electrolytes, weak electrolytes, and then you have non-electrolytes, which I mentioned before. How do we determine, the concentration of ions in an aqueous solution? Well, firstly, let me talk about this symbolism here. This is a symbolism that you're going to meet in chemistry from now till whatever chemistry courses you'll be doing after, right? Square brackets or square parentheses is used to represent the molar concentration of whatever is within the parentheses. So for example, if you see something like this, right? That should be read as the concentration of sodium hydroxide is equal to, let's say, 1.0 M, right? So basically, whenever you see this symbolism, it means the concentration of whatever is within those square parentheses, all right? So in the case of sodium chloride, where the molarity is 0.010 M, we know that sodium chloride, when added to water, and this is true for any ionic compound that dissolves in water, it breaks up. The fancy term that we use in chemistry, we say that it dissociates, right? So when sodium chloride dissociates, it forms sodium ions and chloride ions according to this equation right here. And because of the stoichiometry of this equation, a 1:1:1 mole ratio between the sodium chloride that you start off with and the sodium ions and chloride ions that you end up with, you can predict that the concentration or the molar concentration of sodium ion will be 0.010 M, and the same is true for the concentration of chloride ions, right? So basically, whatever the molarity of the sodium chloride that you start off with would be the same as the ions that you end up with in a solution. And we can further say, I don't think I have that here, but we can further say that the total ion concentration is equal to 0.020 M, which is simply the sum of these two numbers here, all right? So that's how you can determine the ion concentrations in solutions. All you have to do is look at the, well, firstly, what I would do is write down the balanced equation for the dissociation, and then you can look at the stoichiometry to determine the concentrations of the respective ions. Okay, let's talk about acids, and in particular, the two categories of acids, weak acids and strong acids. So here are the definitions. A weak acid is one that undergoes partial dissociation when added to water, right? So we saw one example of that earlier, and that's acetic acid, right? Acetic acid will break up, but only partially. In other words, only a small fraction of the acetic acid molecules will dissociate to form ions, right? And therefore, most of the molecules that remain would be acetic acid molecules. Strong acids, on the other hand, will undergo complete dissociation. What that means, therefore, is that those acids, when you add them to water, all the molecules, all the acid molecules will break up to form ions. So as a result, strong acids are very good conductors of electricity, while weak acids are not as good, all right? And the way we represent the dissociation of strong acids and weak acids in that equation I showed you earlier is that in the case of weak acids, we have arrows pointing in both directions. Now what that means basically, I think I have an example of that here. Right, so here is acetic acid undergoing partial dissociation to form ions. So you'll notice that we have two arrows here pointing in opposite directions, right? Basically what this means is that the acetate and the hydrogen ions will combine to form acetic acid as soon as they're produced. And you're going to reach a stage of what we call dynamic equilibrium. And for those of you who plan to do Chem 2, you're going to learn more about that later on. In that state of dynamic equilibrium, the rate of the forward reaction will be equal to the rate of the reverse reaction, right? So basically you end up with a kind of balance where the concentrations of the ions and the molecule, the acetic acid molecule, remain constant, but there's this underlying back and forth taking place where, for example, as soon as this is produced, it's reacting, and as soon as this is produced, that's reacting, and as soon as this is produced, that's reacting to go the other direction. So the concentrations remain constant. And as you can see here, this is just a ball and stick model representation of the same reaction. All right. So that's basically how organic acids, for example, most organic acids are weak acids. All right, and there are a few inorganic acids that are weak acids as well. Okay. So how do you recognize strong or weak acid, right? Well, one convention, which is not always adhered to, but one convention that is used is that in the case of strong acids, the hydrogen is always written at the front of the formula. Like, for example, in the case of hydrochloric acid and sulfuric acid, but that is not always true, right? In the case of weak acids, they tend to write the dissociating hydrogen at the end of the formula. Again, this is not a hard and fast kind of rule, but that is sometimes what is observed in chemical literature, right? But it's important that you know which acids are strong and which acids are weak. So how do we know that? Well, you need to memorize these acids as strong acids, right? Hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid. So you need to remember these acids as strong acids, all right? And let me just say something about sulfuric acid, because this is kind of special compared to the others, because you'll notice that in the formula of sulfuric acid, there are 2 hydrogen atoms per molecule, right? In the others, there's only 1. The thing about sulfuric acid is that it can lose those 2 hydrogen ions in 2 steps. Let me just show you what I'm talking about. So in the case of sulfuric acid, the first dissociation will release 1 hydrogen ion and what is called the hydrogen sulfate ion, right? Now, I mistakenly put 2 arrows there, but it should only be 1. So let me erase this here. This dissociation is a strong dissociation, so it goes in one direction, right? Now, this here, the hydrogen sulfate ion, can release another hydrogen ion, like this, to form the sulfate ion. In this case, however, this dissociation, second dissociation, is weak. So therefore, you're going to have the back and forth as far as that second step is concerned, right? So you need to remember that in the case of sulfuric acid, the first dissociation is a strong dissociation, right? 100% dissociation going from sulfuric acid to form the hydrogen ion and the hydrogen sulfate ion. But when the hydrogen sulfate ion dissociates itself, that dissociation is going to be a weak dissociation. So therefore, the products that are formed will react with each other to form the HSO4 minus, and you have that back and forth. All right, so that's something you need to remember when it comes to sulfuric acid. But you also need to remember all these 6 acids as strong acids. So if you have a question that you're going to do in a test or assignment, whatever, where the strength of the acid is relevant, then you need to keep this in mind. Pretty much all other acids that you're going to encounter will be weak acids, unless you're told otherwise, all right? Okay.
What are the names of the?
This is hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and this one is called perchloric acid. Okay. Okay. So let's talk about strong and weak bases. If you understand what we said about strong and weak acids, then when it comes to bases, same idea. Strong bases are ionic hydroxides that completely undergo ionization in water, and therefore, as a result, just as in the case of strong acids, they are very good conductors of electricity. Weak bases, on the other hand, do not dissociate as strongly, and therefore, as a result, the concentration of ions in those bases are weak or low, and therefore, the conductivity of these bases will be very weak. All right. So one common example of a weak base would be ammonia. Right, ammonia is a weak base. We have the equation here. No, I don't. Okay, let me show you how ammonia behaves. So when you add ammonia the water, this is what happened. NH3 plus H2O will form NH4 plus OH minus, right? So as you can see, it's a back and forth, right? As soon as the NH4 plus and the OH minus react, they will react to get back to the ammonia and water. So they have the back and forth taking place, right? So as a result, the concentrations of the hydroxide and the ammonium will be very low, and therefore this solution will not be a very good conductor of electricity, right? So that's as far as weak bases and strong bases are concerned. Now, again, you might be asked the question, okay, how do you know which base is strong and which base is weak? Basically, this one is an easier list to memorize because basically these are all the hydroxides of groups 1A and 2A, right? And of course, you'll have access to your periodic tables while you're doing your test and so on. So basically, all these hydroxides are considered to be strong bases, right? Pretty much any other bases would be weak bases, right? Unless you're told otherwise again, all right? Okay, so that's basically it as far as the difference between strong and weak bases and strong and weak acids, all right? Okay, so next we're going to talk about all right, you know what? Let me at least start you off on a little bit more. Here we go. Guys up there in Zoom. Let me see if I had already published. Let me see. Okay, so I've just published for you guys assignment number 4. You just download it here. Okay, so we're going to focus on questions 1 and 2, all right? So it says write equations showing write equations showing how the following strong electrolytes ionizes or dissociates into ions upon dissolving in water. So basically, I'll help you out with the first one. Okay, so in the case of potassium nitrate, KNO3, when it's dissolved in water, this will be solid. So when it's dissolved in water, you're going to get K plus, aqueous, and NO3 minus, aqueous. Right? Okay, so what do you think would be the equation for B? I'm sorry? Mean this?
There's something there.
And O3 and then S for solvent.
Oh, that's false. Yeah, solid, I'm sorry. Okay, what about B? What will be the products upon dissociation? Body? A body?
Fe plus.
Well, what will be the charge? That's the important thing. Fe what? Yeah, but if you're saying +1, that's not correct. You might find that table with the list of ions helpful. in determining the charges of the ions formed. And what would be the next ion? SO4, 2 minus. Okay, very good. Okay, what about the next one? NH4, 2, CO3, solid. By the way, these are aqueous, so make sure you include those states in box, right? Okay, so when that is added to water, what would be the result? Now keep in mind, you have a 2 for the ammonium here, right? So what do you think the products would be? Alright. NH4 plus 1, okay. But how do we account for the 2 here? So you're gonna put a coefficient of 2 here. Right? Aqueous plus what? CO3 minus 2 or 2 minus aqueous. All right. Okay, and then the last one in this series, let me scroll down here. What let me clear this. Okay, NH3 NaHCO3. Okay, solid. When added to water, what would be the result? What would be the ions formed? Na plus, aqueous, and what?
HCO3 negative.
HCO3 minus aqueous. Very good. All right. So that's relatively easy. Any questions about number 1? Any questions? Yes, sir.
So on part C, do we put 2 negative there because that's the sign of the verb to,
Right, because of the sign, you mean for the carbonate?
yeah,
Yeah,
so
that's the charge. That's the charge for the carbonate ion.
on the NH4, if it's 2 H4, does that mean it's the -2 or no?
No, the 2 NH4 has a plus 1 charge,
Okay,
Right.
it doesn't,
but ultimately the charges cancel out. Right? Okay, any other questions? All right, let me clear this here. And let me scroll down. Okay, scroll it down. Okay, now the next question is asking for you to classify each of the following as strong or weak acid or base, all right? So remember what we said about strong acids, strong bases, right? Strong acids, there are 6 acids that you need to memorize as strong acids. And as far as strong bases are concerned, those are the hydroxides of groups 1A and 2A. So, A, is that, let me turn this on. Okay, so in the case of A, is that, well, first, is that an acid or a base?
Acid.
Okay, and what type is it? Strong, so strong acid. What about B?
Strong base.
Strong base. What about C? We just made this one a while ago. Ammonia,
Weak base.
weak base. What about D? Weak acid. All right, very good. All right, so it's very important that you're able to identify these different types of acids and bases, all right? Okay. So now that we have done questions 1 and 2, I don't think we can do questions. No, we can do questions. Okay, so let's continue our discussion. Let me clear this. This, and then move on to the next topic in the PowerPoint. So here now we'll be talking about what we call the neutralization reaction. So basically, neutralization is a term used to describe the reaction between an acid and a base. And the reason why it's called neutralization is because the whole idea behind it is that you have acids, which are acidic, you have bases, which are basic, but when they react with each other, supposedly, they cancel out each other's properties. So the resulting products of the reaction is expected to be neutral. Now, let me just say that that is not always true, but I won't get into that because that, again, is another topic that you're going to meet in Chem 2, right? But for now, let's assume that's the case, right? Let's assume that whatever the acid and bases that are reacting with each other, the resulting products will be neutral, right? And in this context, there are two products that are formed, one of which is water, and the other one which is called a salt. And the formula of the salt is dependent on the formula of the acid and the base that you start off with in the beginning. Now, in this particular case, we're starting off with hydrochloric acid, and you're reacting it with potassium hydroxide. Now, the water is formed as a result of the hydrogen coming together with the hydroxide, and that's how we end up with the water, right? Now, whatever is left will themselves combine, which is in this case is the potassium and the chloride, will combine to form the potassium chloride, right? So the salt that is formed as a result of the positive part of the base coming together with the negative part of the acid, right? And that's how you end up with the salt being formed, right? And there's another statement down here which talks about the use of indicators, which, if I'm not mistaken, in our lab, we're going to do a titration where basically you add a substance to the reaction to show when you add the right amount of, let's say, base to the acid or acid to the base, all right? But that's all I'm going to say about it, right? So let's talk about how we write down what is called the net ionic equations for a neutralization reaction, right? Now, in order for us to do that, what we need to do is identify those species that remain unchanged on both sides of the equation, right? We call those species spectator ions. They're spectator ions because they do not take part actively in the reaction itself. The participants in the reactions are the ones that actually are involved directly and result in product formation. So, going back to this example, the reaction between hydrochloric acid and potassium hydroxide, excuse me, to form water and potassium chloride, right? Now, the first thing, by the way, this is called the molecular equation, which is a bit of a misnomer, but in most textbooks, that's the term that they use, molecular equation, all right? It's a bit of a misnomer because not every species involved is a molecule. Potassium chloride is not a molecule, but that's a term that everybody's using. So we're going to call this equation the molecular equation. Now, in order for us to determine the net ionic equation, what we have to do first is convert the molecular equation that you see here to what is called the ionic equation. And the ionic equation is basically showing you which ions are actually present in a solution. Now, in order for us to determine that, we have to identify if there are any strong acids present in the reaction, if there are any strong bases present also, and if there's any ionic compounds in aqueous solutions, right? So here we have HCl. We all know by now HCl is a strong acid, right? So because it's a strong acid, it will undergo complete dissociation. The same is true for potassium hydroxide. It's a strong base, so that will undergo complete dissociation. The water, on the other hand, is a molecular compound. That will not undergo any dissociation, so that will remain intact, right? And then we have potassium chloride in an aqueous solution, right? Any ionic compound, and you may want to write this down, any ionic compound in an aqueous solution will undergo complete dissociation. Any or all ionic compounds, when dissolved in water, will undergo complete dissociation. Right? Very important for you to recognize that. And that's what's going to happen in this case. So how do we get from the molecular equation to the ionic equation? We basically break up all the compounds we expect to undergo complete dissociation. The strong acid, the strong bases, and the ionic compound in an aqueous solution. And this will be the result, right? The HCl here will break up to form H plus and Cl minus, right? The potassium hydroxide will dissociate to form K plus and OH minus, right? The water is a molecular compound. That will not break up. That will remain intact. And then we have the potassium chloride, which is an ionic compound in an aqueous solution. That will undergo complete dissociation as well. So we call this equation here, let me write it here, the ionic equation. All right, the ionic equation basically shows you all the ions that will be present in this solution, either as reactant or product. All right. So now we're going to get to what we're working towards, the net ionic equation. How do we get the net ionic equation? As I said before, we need to identify what is called, or what are called, the spectator ions. The spectator ions in the ionic equation remain unchanged as you go from left to right. So in this particular case, you'll notice that you have a chloride here and a chloride here. So the chloride ion will be the spectator ion, right? Or will be one of spectator ions present. If you notice also potassium, you have potassium K plus here, and you also have K plus here. So those are spectator ions. So what we can do, because they appear on both sides of the equation, we can cancel them out. The chlorides will cancel out, and the potassium ions will cancel out, right? And then what we'll be left with would be the net ionic equation, which is simply the H plus and the OH minus coming together to form the H2O, and that's it. And that's how you determine the net ionic equation for this reaction. All right? Okay, any questions about it? Any questions? Same thing. Same thing there. All right, any other questions? Any other questions? What is the what? Oh, no, that's L. I'm sorry. That's liquid. Sorry. Okay, any other questions? Any other questions? Okay, we're going to need this later on in the context of other reactions, but for now, this is what we're using as applied to neutralization reaction, right? The reaction between an acid and a base to form your salt and water, right? So basically what this is showing is that ultimately the reaction between an acid and a base is simply the reaction between the H plus ion and the OH minus ions to form water, right? Okay. You look puzzled. What's wrong? Okay. All right. So this slide here is describing. I won't spend much time on this because you'll actually learn this in the lab. We'll be doing this in the lab. There's a technique known as titration, which is basically used to determine several things. I think in the experiment that you guys will be doing, we'll be determining the concentration of one solution based on the concentration of a known solution or the known concentration of another solution. And you have different types of titration. You have acid-base titration, you have redox titration, you have precipitation titration, you have different types. The one that you'll be doing in the lab is known as acid-base titration because this will involve a reaction between an acid and a base, right? So I'm just going to briefly go over how this works. Basically, you're going to have several pieces of apparatus. One is known as a burette. Let me see if I can pull up a picture of a burette here so that you can see what it looks like. It's a long cylindrical piece of glassware. Okay, so this is from a company. Okay. Unfortunately, this one does not show you the graduation marks, but basically this is what it looks like. You have a cap with a nozzle right here. They come in different sizes. I think the smallest one I've seen is a 25 mil. This one is more common. I think it's a 50 mil burette. And one thing, in fact, you know something, let me see if I can find a better picture. Okay, let me see if this will work. Okay, so, yeah, they come in different sizes. And you can see in this particular picture right here, right? The way it's graduated, well, they don't show it. Okay, so here's the top, right? The way it's graduated, it starts at 0 at the top, and it increases, the numbers increases as you go down, right? That is kind of different from what you're probably used to when it comes to measuring cylinders, where it starts at 0 at the bottom and goes up to the top. So this one is a 50 mil burette, starts at 0 at the top and goes down, right? So it's important that you understand that the way this works is that you're not measuring the amount of liquid that's in it, right? When you pour liquid, when you pour, you know, let's say sodium hydroxide or whatever, it's used to measure the amount of liquid that is dispensed from it, right? That's how we use it, okay? And you're going to see how that works. So that's one important piece of glassware that is used in this type of experiment. Another important piece of glassware is what is known as a pipette. And let me see if I can bring up an image of one here. And there are different types of pipette, but the one that we use for this purpose is, again, a piece of cylindrical glassware. They come in different sizes again. The smallest one I've seen, I think, is a 5 mil one. This one that I'm putting up here is a 25 mil pipette. Okay, they're not showing the full picture of this here. Okay, let me see if I can find. Okay, these are several, hold on. Okay, so these are several pipettes that you can use to dispense liquids of different volumes, right? There are some pipettes that have a set volume that they can measure, right? 10 mil, 5 mil, 20 mil, 25 mil, and so on. So basically, what you do is you take the tip. Well, firstly, you put what is called a pipette filler, which is basically an instrument that is used to draw the liquid up. Then you put the tip of your pipette into your solution, and then you pull the liquid up. And then if it's like one of those set volume readings or etched on the stem of the pipette, you just pull it up to that line, and then you transfer that to whatever container, beaker, flask, or whatever, right? So that's another important piece of glassware that is used in this process. So basically the way this works is that one reactant is placed in a burette, and the other reactant is placed in a flask along with a few drops of your indicator. And then what you do is deliver your solution from the burette. Well, firstly, you need to record the initial volume reading on the meniscus, where the meniscus is in the burette. And then you start adding your solution through the tip into the solution in the flask, and then you swirl it until you end up with the color change occurring. And the color change occurring is dependent on the indicator that you're going to use. The indicator that you'll be using in this experiment is one known as phenolphthalein, which is colorless in acid and pink in base, right? So if your acid solution is in the flask to begin with, and you add 2 drops of your indicator, there will be no color change, right? Because that's the color of the indicator in an acid environment. But when you start adding your base, then what will happen eventually is that you're going to see a pink color appear and then disappears upon swirling, and appear and then disappears upon swirling when you add more. And then that will continue until 1 drop turns the entire solution pink. That's when you stop adding your base, and then you take your readings, and then you can do some calculations based on that. So for those of you enrolled in my lab, you'll have experience in doing that, right? Okay. All right, so let me talk about gas forming reactions. So there's some reactions, and these are acid-base reactions, where gases are produced spontaneously when you add acid to certain ions, right? For the first two, for the first two indicated here, bicarbonate and carbonate, if you add acid to it, then you're going to end up with carbon dioxide and water being produced, right? And this is something you can do at home. As you can see here in this picture, the bicarbonate ion is present in baking soda. Baking soda is basically sodium bicarbonate. When you squirt some lemon juice, or you can add some vinegar, you're gonna see the same thing. You're gonna see foaming. The foaming is as a result of carbon dioxide being produced, right? So that's one example of a gas forming acid-base reaction. Another example is the reaction between acid and any compound containing the sulfide or hydrogen sulfide ions. Now, this one I would not recommend that you do at home because the gases or the gas that is produced is sulfur dioxide. And if you're in a room filled with sulfur dioxide, then you start choking and all that. So you want to avoid that. But you need to know that this is another example of an acid-base reaction that produces the gas. And then we get to this pair of ions here, the hydrogen sulfide or sulfide ions. When you add acid to any one of these, this produces a gas known as hydrogen sulfide. Now, this is one reaction you definitely don't want to do at home. Because one, hydrogen sulfide is a very awful smelling gas. It's a smell of rotten eggs, right? In fact, the rotten egg smell that we associate with eggs, the proteins being decomposed, that smell is due to hydrogen sulfide gas being produced when we have the proteins undergoing degradation, right? Another thing about this gas too is that it's toxic, right? So again, for those two reasons, you don't want to do that at home. So these are all examples of acid-base reactions where gases are produced, all right? Okay, let's talk about precipitation reactions. Now, precipitation reactions are reactions where you take two solutions containing two ionic compounds, right? And you mix them together and you have the spontaneous formation of a solid, right? And I think the example that is shown here is the reaction between, if I'm not mistaken, lead to iodide and, no, I'm sorry. Lead to iodide is a product. Potassium iodide, which is aqueous, and lead to nitrate, which is also aqueous, right? And then this will be a double displacement reaction, right? Where there's a switching of ions. So the resulting product will be lead to iodide, which is a solid, and potassium nitrate, which is aqueous, right? And to balance this, we need a 2 here and a 2 here, all right? So this is an example of a precipitation reaction because here we're starting with this solution, we're mixing it with this solution, and you're going to get a solid being formed. And the solid, this yellow, pale yellow color solid, is lead iodide being formed, right? The other product will be potassium nitrate, but that will remain in solution, right? So this is a good example of a precipitation reaction where two solutions are mixed and you end up with a solid that is formed. And by the way, the solid that is formed, we call that a precipitate. Let me put that here. So the solid that is formed here, we call it a precipitate. Right? So that's basically how that works. Now, if you recall, we determined through several steps the net ionic equation for a neutralization reaction. We can do the same thing for a precipitation reaction. So that's what we're going to do now. I'm going to show you how to do that. Oh, before we do that, very important. This is a very important chart that you're going to need in order for you to determine the net ionic equation for a precipitation reaction. In fact, we're going to use this to determine or make a prediction as to whether or not a particular ionic compound is a solid or will it dissolve in water. That's very important in order for you to determine whether or not you're dealing with a precipitation reaction. And this chart, by the way, is available in your tables. And of course, you'll have access to it during your tests so that you can have it to refer to. So you're going to see how this works. Let me get out of this here. And let me, word. Okay, so. Okay, so this is the equation that I just showed you. It is, potassium iodide, ABS, plus lead 2 nitrate. Let me just emphasize again the importance of state symbols. Please do not neglect the use of state symbols in these equations, right? Now, one of the products is, as I said before, lead 2 iodide, and the other product is potassium nitrate, aqueous, right? And to balance this, and again, let me emphasize also the equation that you start off with must be a balanced equation, right? So that will become important as you're going to see when we get from the molecular equation, which is what this is. Again, this is a bit of a misnomer. Molecular equation, right? Okay, so how do we get from the molecular to the ionic? Now, if you remember what I said earlier, when we were dealing with the neutralization reaction, remember I said that any ionic compound that is in an aqueous solution will undergo complete dissociation. Any ionic compound that is in an aqueous solution will undergo complete dissociation. Now, potassium iodide is ionic and it's in an aqueous solution, so we know that that will dissociate to form the ions. But you have to also keep in mind that there's a 2 here, right? So when this dissociates, you're going to end up with 2K plus aqueous plus 2I minus aqueous to give, well, not to give, that's it, as far as the potassium iodide is concerned. Then we do the same thing with the lead 2 nitrate. That will also dissociate because it's ionic and it's in an aqueous solution. So when that dissociates, you're going to end up with Pb 2 plus aqueous plus 2NO3 minus aqueous, right? So that's basically how we take care of things on the left side of the equation. Let's look at the right side. Now, what do we notice here? In the case of lead iodide, lead 2 iodide, it's a solid. It's not in an aqueous solution. So therefore, that will not dissociate. So we simply rewrite this as PbI2 solid, right? And then we get to the potassium nitrate, which is ionic and in an aqueous solution. And we have a 2 here. We have to take that into account. So basically, that will split up to form 2K plus aqueous plus 2NO3 minus aqueous. All right? So this would be the ionic equation. So the next step is the net ionic equation. Now, let me see if you remember what I said about obtaining the net ionic equation. How do we get from the ionic equation to the net ionic equation? We cancel out the, exactly, in other words, the spectator ions, right? Okay, so in this particular case, what are the spectator ions you can identify? Okay, 2K plus, anything else? Nitrates here and here. And there's nothing else that will be, you'll be able to cancel out. So basically, we write out what is left, 2I minus aqueous plus Pb 2 plus aqueous. And on the right side, we're going to have Pb I2 solid. And that would be the net ionic equation for this reaction. All right? Any questions about this? Okay, so let's see. Oh, one more thing I need to say. In some questions that you may get, you may not be given the products, and you'll have to figure out what the products are. which in the case of a reaction like this, it's very simple, it's just switching off ions, right? Let me give you another example, but I want to make sure you understand. Can I erase this? All right, so let me, so this example I'm going to make up, I'm only going to give you the two reactants. Okay. BaNO3 2 plus Na2SO4, all right? And these are both aqueous. Right? So let's say I gave you that, and I ask you to write down, eventually, determine the net ionic equation. So the first thing you have to do is figure out what the original equation is, right? So as I said before, it's a switching of the ions, right? So what will happen is that the barium will come together with the sulfate. So you have to figure out the formula for that result, and that would be barium sulfate, BaSO4, right? And then the sodium will come together with the nitrate to form sodium nitrate, right? And then we have to balance it. So to balance this, we're going to need a 2 here, and I think that's all you're going to need, all right? So now that we have done that, the next step is to determine which of the two products, if any, would be insoluble. How do we do that? We go to the table that I showed you earlier. Let me see if I can bring it up here. The chart I showed you earlier. This chart right here, which had a split screen situation. But anyway, so this is the chart that you're going to use to make predictions as to whether or not your products are soluble in water, right? So one of the products was barium sulfate, right? And according to this chart, most sulfates are soluble, but we have certain exceptions. One of which is barium sulfate, right? So therefore, we can go to this equation, and since we know that barium sulfate is insoluble based on the chart, we put S there. S stands for solid, which means that it did not dissolve in water, right? So that's how we use the chart. We have to also figure out, based on the chart, if sodium nitrate is soluble in water. So we go back to the chart. And what does the chart say? The chart says that almost all nitrates and group 1A metal salts are soluble, right? And sodium nitrate fits into those two categories. So therefore, we can say that the sodium nitrate, beside it, we'll put AQ, which means that it's dissolved in water, right? Which is important for us to determine the net ionic equation. So once we determine that, this is the molecular equation, right? So my question to you is, how do we determine the ionic equation, which is the next step, based on what we have done so far? How would we determine the ionic equation? Okay, so what do we break down? Let's start here. Do we break this down? Do we break this down? Do we dissociate it? Yes, because one, it's ionic, and two, it's in an aqueous solution, right? So when this dissociates, it's going to form Ba2 plus aqueous. And because of this 2 here, you're going to get 2NO3 minus aqueous. All right? So that takes care of this. Then we have Na2SO4, right? It's ionic and aqueous. So when that dissociates, you're going to end up with 2Na plus aqueous and SO4 2 minus aqueous. All right? Okay, so that takes care of things on the left side. What about the right side? Do we break that down? Does that dissociate? No, because it's a solid. So we just simply rewrite this as it is. And then what about the sodium nitrate? Will that dissociate? It will dissociate. So when it dissociates, it forms 2Na plus aqueous plus 2NO3 minus aqueous. Okay, what's the next step? Okay, so what are the spectator ions we can identify in this case? I'm sorry? Two nitrates, okay, they can go. Anything else?
Sodium.
The two sodiums that will go, and that's it. So basically, the net ionic equation will be Da 2 plus aqueous plus SO4 2 minus aqueous to give Da SO4 solid. And that would be the final answer, right? So you could be given a question where you're given the two reactants, right? And then you have to figure out what the products are, then exchange. Then once you get the balance equation to begin with, which would be the molecular equation, then you get the ionic equation where you identify which species will undergo dissociation to form ions. And then you identify the spectator ions, you cancel them out, whatever remains, that would be the net ionic equation, all right? Okay, any questions about it? Any questions? Any questions? Okay, going back to the PowerPoint. So as I said before, this particular chart you'll have access to. I would suggest that you familiarize yourself with it so that you know how to use it when you get to these kinds of questions. This is just some examples of precipitation reactions that has some industrial applications. I won't go through all of them, but like the first one is where we use aluminum ions to precipitate the hydroxide ions out of solution. Or this one here, which is used in photography, and so on and so forth. So just goes to show you that these types of reactions have some, applications which are useful. Okay, let's talk about what time is it?
10:30.
10:30. Okay, at least I can start talking about this. Okay, so now we're going to get into a discussion of what we call oxidation and reduction reaction. We use a short way of expressing that as redox. So whenever you hear the term redox, we're talking about oxidation or reduction in this context. So basically, there are several ways of defining redox reaction, but it really comes down to what you see right here. The transfer of electrons from something to something, from one reactant to another, and then you have the product being formed as a result of that, right? So the substance that is undergoing electron loss, we say that substance is being oxidized, and the substance that is undergoing electron gain, we say that substance is being reduced. And there is a mnemonic that is used to remember. You might find this helpful. Oil rig, right? Oxidation involves loss of electrons. Reduction involves gain of electrons, right? I don't know if that helps, right? But you can use that to help you to remember the difference between the two, all right? So that's basically what is involved in redox reaction, right? Now, in order for us to understand what is happening when it comes to redox reaction, there are some rules for determining what is called the oxidation number of an atom in a molecule or ionic compound. So what is this term? What does that mean? The oxidation number is basically the charge an atom would have in a molecule or in an ionic compound if the electrons were completely transferred, all right? And this is basically used as a tool, or as a measure, I should say, of the level of oxidation of a particular atom that is present in a molecule or ion. So there are some rules that you have to know. What you'll find is that you don't need to sit down and memorize these rules. Basically, if you use these rules over and over again, they become second nature. All right, so let me just go through these rules. The first of which is free elements. Any elements by themselves, not combined with anything else, those elements automatically will be assigned an oxidation number of 0, right? So sodium, magnesium, oxygen by themselves, not combined with anything else, you can assume that the oxidation number of those elements would be 0. So these are just some other examples, right? The next rule has to do with monatomic ions, right? If you're dealing with a monatomic ion, whatever the charge is on that ion, then that would be the oxidation state or oxidation number of that ion or of that element, right? So for example, the lithium ion has an oxidation number +1, the iron 3 ion has an oxidation state of +3, and the oxide ion has an oxidation number -2. So any monoatomic ion, whatever the charge is, that would be the oxidation number. The next rule, the oxidation number, and this rule has specifically dealing with oxygen. It says here that the oxidation number of oxygen is usually -2, excepting in the case of peroxides or any compound that contains the peroxide ion. In those instances, the oxidation number is -1, right? So if oxygen, and I probably should add here, if oxygen is combined with something, not oxygen by itself, right? So you may want to make a little note of that, right? So if oxygen is combined with something else, right? The oxidation number of oxygen in that particular compound is -2 unless it's either a peroxide you're dealing with or hydrogen peroxide, right? In those instances, in the case of peroxides and hydrogen peroxides, the oxidation number of oxygen in those compounds would be -1, all right? Okay, the fourth rule has to do with hydrogen, right? The oxidation number of hydrogens, again, when combined with something else, is equal to +1, excepting if the hydrogen is bonded to a metal in binary compounds, in which case the oxidation number of hydrogen in those compounds is -1, all right? Do I have any examples here? No, I don't. Okay, let me write one down. So for example, in the case of, let's say, HCl, the oxidation number of hydrogen is +1. But if you have, let's say, lithium hydride, the oxidation number of hydrogen is -1, all right? So it all depends on what hydrogen is bonded, all right? Okay, the next rule says, again, we're talking about these compounds or these elements being part of compounds. Group 1A metals, their oxidation number is +1. Group 2A metals, their oxidation number is +2. And fluorine is always -1. And let me just add here, when these elements are in compounds, right? So if these elements are combined with other elements to form compounds, then in the case of group 1A metals, their oxidation number is +1. In the case of group 2A metals, their oxidation number is +2. And fluorine is always -1 when it's combined with other elements, all right? Let me see, are there any other rules? Oh, okay, so this one says, the sum of the oxidation number of all the atoms in a molecule or ion is equal to the charge on that molecule or ion, all right? So this is helpful when it comes to determining the oxidation numbers of elements that are not covered in the previous 5 rules, all right? And I think I have an example of this here. So let's look at this example. This question is asking, what are the oxidation numbers of all the atoms in the bicarbonate ion? Well, directly speaking, we can tell that the oxidation number of hydrogen is +1 because we saw that explained in rule number 4, right? So hydrogen is +1, and also we know that oxygen is -2, again, based on the rule that we saw in rule number 4. And then now we get to the carbon. So how do we determine the carbon? Well, that's where rule number 6 comes into play. Because rule number 6 says that the sum of all the oxidation numbers will be equal to the sum of all the oxidation numbers of all the atoms involved will be equal to the total charge on the structure, in this case, the ion. So we set up an equation, right? We know that oxygen is -2, we know that hydrogen is +1. We don't know directly what carbon is, so we're just going to call that a question sign. So we just add up the oxidation numbers of oxygen times 3 because you have 3 of them, +1 for the hydrogen, plus we don't know what that is, but the sum of that we know is equal to -1 because that's the overall charge. And therefore, all we need to do is find out what this is, and it turns out that the oxidation number of carbon is +4, right? And that's how we can determine the oxidation number of any other elements that's not mentioned in the previous rules, all right? Okay, I'm gonna stop here. What I would suggest you do is that based on what we have covered so far, you should try questions 3, 4, and 5. 3, 4, and 5, all right? If you have any problems while doing those, please let me know. Let me remind you also of your test on Thursday, which will cover chapters 1 and 2, all right?
Will you go back one slide,
Yes,
please,
sir.
to show, number 3 there?
Okay. All right, so that's pretty much it for today. So I'll see you guys on Thursday. Oh, sorry. All right, for you guys out there in Zoom, I'll be signing off now.